So the first paper that I'm going to present is latent diffusion, also known as stable diffusion. But, well, the paper is high resolution image synthesis with latent diffusion models. This is a collaboration between LMU and another university in Germany. This is a CVPR paper for this year in the main conference. And also another fact that I found interesting is that this is a collaboration with Runway, which is a video clip editor company. So this project has these important collaborations, and this is why they treat.
So Bjorn, I met Bjorn when I was at Berkeley. He was a postdoc there, and so he was a professor at Heidelberg until very recently, when he moved to München, but not to TUM, but to the second university in Munich, which is this one. So Bjorn's work is very a little theoretical, I would say, and he has always worked in recognition until recently. So he's very strong on the technical side. He publishes a lot in NeurIPS, and we are now collaborating with one of his former students in the projects with Meta Reality Labs Zurich.
So before we start with diffusion models, we prepare a little introduction about what are generative models and specifically what are diffusion models precisely. So the two papers are oriented for images or the 2D domain, but these models also work for one-dimensional data such as signals for the electronics. So we have different kinds of generative models. So the first models that we have are GANs, that basically we have a generator and we have a discriminator that is trying to evaluate how good the images that I'm generating are. So basically my generator focus from transforms some information C that is commonly noise, random noise, a Gaussian noise, into an image. And then the discriminator is going to evaluate how well that generation is as a classifier. The other kind of generative models are bias, that are variational autoencoders. That what these models are is try to maximize the variational lower bound, which is basically dimensional reduction. So I part from one image, then I encode that image into a latent representation C, and then I decode this latent representation and I try to reconstruct the input image. But these models have a regularization term that help us to reconstruct better this latent space. Another type is flow-based models that basically are models that are invertible. So I'm using the same model for encode and decode. And also is a reduction, and here we have latent space. And finally, we have the new generative models that are diffusion models. What is the difference? See, where is the latent space here? So GAN starts from the latent space. Encoders, autoencoders, and flow-based models first encode, and then they create a latent space with a different resolution. But what happens in diffusion models? The latent space has the same dimension that the input. This is something very important. And here, what we have is that we have a forward process in which we are going from one x0, that is my image, into a latent representation, and then what I'm trying to do is go backward from my vector C or my representation to the original image. And this is known as a Markov chain process. Why? So if I start from here, then I have to perform some process several times, T times to be specific, and each time only depends from the previous step. So this is why we consider this architecture as a Markov chain because the actual state only depends from the previous one. So as comparison, we have high quality samples, fast sampling, and diversity, and how easy is for these models to be trained. So generative adversarial networks generates high quality samples, and they generate as fast, but they have issues in how diversity the images that they generate are. In the other hand, we have the variational autoencoders and normalizing flows that are fast and that diversity, but the images do not have high quality. And finally, we have the denoising diffusion models that intersect high quality samples with a lot of diversity, but they fail in the fast sampling. And I'm going to show why this is an issue. And the paper that I'm going to explain solves this problem. The computation time, and the software requirements. So, since we are here evaluating image generation, we want to see if my model is able to generate different styles of the images. That's how we define if a model can be diverse. So let's imagine that we have this image of the dog. Then we can add the times a Gaussian noise, and then we can add at the end of several time steps with absolutely random noise, right? We can do this, and this process is fixed. We just generate random noise and we add them several times. But the intuition behind diffusion models is what happened if we learn to do the opposite process. So what happened if I learn how to go from this random noise to the original image? So if I can go from the image to the random noise, how can I do to go from the random noise to the image? And this is basically the intuition behind diffusion models. So the first step is the forward diffusion, and this step is fixed. So I start with an image, X0, and several times I add a Gaussian noise, big T times, and at the end, I end up with a random noise. And this noise can be computed with the mean and the standard deviation of a distribution, of a Gaussian distribution, to compute the noise conditioned by the previous step. And this is step by step. And since this process is fixed, we can put it all together in one single expression, because we have the absolute control of all the process. And then we can have this expression behind that is just like the overview of all the process. So basically, I'm starting from X0, and I want to go from X1 to X big T. So these expressions presumes all my forward process. So I'm adding random noise each step, just conditioning by the previous step. So the interesting part is the reverse diffusion. So in here, what we are trying to do is that we want to compute the probability distribution conditionated from my previous T minus 1, conditionated by my actual steps. So I'm here and I want to compute the probability distribution from the previous step, right? And how initially they solve this problem is that we need to parameterize the mean and the variance of the distributions. And the way we do that is that we use a neural network that models the mean and variance of my Gaussian distribution. And that's how we learn the noise of the previous step. And as we do for the forward process, here we can also resume all the TB times in just one expressions. But here, pay attention that we are conditioning a probability distribution P theta that is parameterized by the standard deviation and the mean. But here's something important. And instead of computing the image plus the noise from the previous step, we are just going to focus on compute the noise. And what my neural network is going to do is to predict the noise that I just apply in the previous step to get to my current state. So we are just focusing on computing the noise from the previous step. And if we add that noise to the previous, well, it turns out to be in my current state. Is that clear? Yep. Okay. How do they work? Basically, they use a unit architecture because we need to, if you remember, one principal component is that the latent space must be the same dimensionality from the input, right? So this unit architecture basically performs a dimensionality reduction, but the input has the same dimensions, and the output, sorry, has the same dimension. So this is why they show this unit, and they perform deferred adjustments. They use skip connections. They use skip connections and some attentions with transformers that I'm going to explain later. But basically, the neural network that is going to predict the noise is this unit in the backward process. So this works for generation, but in the generation field, we want to generate conditioned images. And this is basically, if I want to generate an image of an Arctic fox, I need to somehow condition my generation to generate that particular image. So we can like guide the generation process. So for guided diffusion, what we do is that we condition the generation. So my probability distribution is now parameterized by the mean, by these parameters, but is conditioned with some additional information that is y. This information can be text, can be another image, can be annotations. And what we do is that we encode this y information, additional information, into the network. I'm going to show you how they do this to conditioning the generation. Yeah, so in the reverse step, epsilon theta is going to be the noise, that is the actual output that the unit is going to predict. And this noise is going to be conditioned by xt. So I have my current state, t, that is the time step in which I'm trying to go back. And now, well, it's going to be conditioned by the condition y. And thanks to guided diffusions, we can do a lot of stuff. We can do semantic generation, in which we pass from a label to a real image. We can have inpainting, text to image translation. And this is one particular I found interesting because I haven't seen this before, which is passing from detection annotations to real images. So I don't know if you can see well, but here blue box is like a plant. And in that exact position, well, the network is able to generate a plant and a vessel. So this I found interesting personally because I haven't seen before. So now that you know a little bit about diffusion models, let's start with the stable diffusions or latent diffusion models, which is the paper. So as far as I told you, the traditional diffusion model works in this way. We have an input, I pass from a unit, and I predict an output. Remember that it is in the reverse process, in the reverse diffusion. But here, if we are treating with high resolution images, like 1024 by 1024 images, the output is going to be the same size. So as you can imagine, if we have to apply this step several times, this can consume a lot of resources in time and in hardware resources. So, and this is a limitation because if these methods require massive hardware, they're only available to a small fraction of the field, which is the huge companies like Meta, Google, and all the companies that have the the money to afford the infrastructure. And also I find interesting that has huge carbon footprint because we need a lot of hardware. And another limitation is because of this, evaluating and training these models are expensive in time and memory. One solution is what authors in Glide propose. This is, okay, my input I heard dimensionally, but I'm going to use a downsample network to get the same image in a lower resolution. So here we pass from 1024 to 56. Then I'm going to do the forward and backward process of my diffusion models in this dimensionality, which is less than my original input. And then I'm going to use an upsample network to go back to my original resolution. So I will say that this is the naive approach because the network, the downsample network and the upsample networks need to be trained. Here's a super resolution approach in which we want to reconstruct this image in a higher resolution, but we can miss some details, some semantic information. But this is the first approach and the first try to reduce the amount of resources and memory that diffusion models takes. But what the authors propose with LDMs is this approach. So if you remember autoencoders, what we have is that we have an encoder, we have an image, and my encoder is going to embed my input into some latent space. So let's say that blue box behind. Now I'm going to perform this diffusion process in the latent representation. And this is different from the previous approach because here we are not treating the input images with a lower resolution, but we are treating the latent representation that should have enough semantic information from the dimensionality reduction. So under this, well, we add the noise several times, we perform the unit, and at the end, we just have a decoder that is going to reconstruct from the latent space the input. So this is the big difference between LDMs and all the other approaches that has tried to reduce the computational requirements that these models have. Yeah, that's it. So, well, as I already said, we apply the diffusion process in the latent representation in pretrained autoencoders. I'm going to explain how they pertain these autoencoders later. So these contributions are different from the authors because the authors have like 6 contributions, but I just resume it in 4. So the training diffusion models on low dimensionality, which is the latent space, and these allow us to create new models that have fewer complexity while preserving the details. The other contribution is that with these models, they can apply to different tasks, such as unconditional image synthesis, inpainting, super resolution, text-to-image translation. So these models can be applied in several of tasks. And they also design a purpose conditioning mechanism based on cross attention. I'm going to explain that later. They use transformers into the unit to conditionate the outputs. And this is how they are able to perform text-to-image generation. And at the end, well, the authors release the code or the protein weights. And some contribution is that since we are now dealing with the latent space, everyone can run this. If you have one GPU with 8 gigabytes, you can run this. So now this is like available for everybody, and you don't have to buy like a lot of hardware. So about the related work, I also told you about the traditional generative approach and how these diffusion models are different. So keep in mind that the lack of diffusion models were that they don't have a fast sampling. They take a lot of time to train and to evaluate. This approach solves this limitation. And there are also some other architectures that are two-stage image synthesis in which they combine autoregressive models with variational autoencoders or autoregressive models with GANs. But this is a two-stage approach. So then I first do something and then I refine that with another approach, which is with a GAN or a VAR. But the LDMs prevent the trade-off and are able to scale more gently because they work in a low dimensional space. And because they use a convolutional backbone. And this is interesting because they use a unit that it has an attention mechanism with transformers, but basically is a convolutional backbone. So the requirements are lower. So about the precise method, what we do, the first step is train an autoencoder, and they call this stage perceptual image compression. So what we want is that from an image X, we have an encoder and a decoder, and then I use this encoder to go from my image space to a latent representation space and go back. And they reduce the dimensions by a factor of F to see how must be the reduction in order to generate a high resolution image. And then train these perceptual laws with a perceptual loss and a patch-based adversarial objective. In generation tasks, is commonly used a loss that is based on pixel space, in which we compare the input against the output at the pixel space. And this is known as L1 or L2 losses or distances. These approaches produce soft images that suffer from smoothness. And this is why they use a perceptual loss, because with the perceptual loss, they are trying to focus on the image quality. And that's the difference. So what are going to be our objective with diffusion models? So if you remember, I talked to you about this epsilon. So what the network is going to do is trying to predict the noise epsilon. So we have the actual noise that I apply in the forward process because I know how to do this. Remember that it's a fixed process. Then I'm going to use the difference between the noise that I predict with my unit that is parameterized by theta with the actual noise that was added to the image. This is for denoising diffusion models, but in LDMs, it's basically the same, but we are not computing in the X or in the image domain, but the difference are that we are using the latent space. So this is the encoder, and this is how the output of the encoder of the input image, which is Z, if you remember. And then, well, the epsilon is now to be computed with the Z at the time t, which is my latent representation. For all of the rest is the same objective function. And this is important because somehow the network needs to know in which step we are trying to predict the noise. Because if you remember, if we go deeper in the diffusion process, the noise is going to be harder or stronger, sorry. So we need a way that the unit, because the unit is the same for all the steps in the diffusion, so the weights are shared, a way to tell the unit, okay, I'm trying to predict the noise from the first step, the second step. And they do this conditioning by this T, in which they compute a sinusoidal vector embedded with this time T. And then they inject this into the unit, and that's how the unit actually knows in which step it is. And now we have the conditioning mechanism. So if we want to perform all of the tasks that I talked you about, conditioning image generation, text to image generation, inpainting, we need a way to condition the generation. And if you remember, what I told you is that now we are going to predict my epsilon theta based on the latent space, the time step, the time step, and one additional information, y, that is going to condition my generation. So what the authors do to perform all these tasks is that they use, they preprocess the conditional information with a domain-specific encoder, which is this one. So for text, they use BERT transformers. For image conditioning, they used a convolution approach. And basically what this is going to do is like encode my condition. So I have a condition that I want to be present in my generation. Then I encode this condition into some representation and I inject this condition by a cross-attention mechanism in my unit. How we inject this? So here is the attention function, which is, yeah. I think this is missing a B here. Yeah. Well, sorry. So we have the softmax function, then we have some queries, the transpose of the keys divided by the dimension of these two matrices. And then it should be like all of this is multiplied by value vector, which is a V. Sorry about that mistake. So this is the general formula for attention mechanism that transformer uses. But how do we inject the conditioning into the attention mechanism? So, well, basically for the cues and the keys, we are going, for the cues and the values, we are now multiplying my matrices by the encoding from the domain specific architecture. So these two are depend on the conditional information, and the queries is going to depend from this cheating. And this is all what I explained you. So basically, we start from an image X and we have an encoder from our variational autoencoder, and we get some representation in the latent space. In this space, we are going to perform the forward and backward process of the diffusion model. But we want to condition in this generation with some labels, which could be a semantic map, text, images. So what we do is that we take this condition, pass it through the encoder, through the domain-specific encoder, and we get some representation here that I can inject in every step of the attention mechanism through my unit. So here we have the queries, the keys, and the values from the attention mechanism. And remember that I inject the embedded representation of my condition through the attention mechanism. And all the rest is, well, I perform these steps several times, to be precisely big T times. I do this same operation. Then I end up with a new latent vector C, and then I reconstruct this latent vector through my decoder to get the final output that should be similar to my input, or that should be conditionated by some of these architectures. And yep.
Are the weights of the unit shared each time step?
Yeah. Yeah, so this unit is the same for all the steps. So basically you just have one unit with the skip connections and with the cross attention mechanism.
Do you know what
Yeah, this one, right? So basically, this is telling us that we first inject the representation of the predict of the condition at the first before they enter to the unit, and then I pass it through all the attention layers.
If that switch resembles something like live method, I probability of actually using the label and not using it. Because these methods usually train sometimes with the label, but sometimes without the label, and then they just like do this formulation of when to use one, when to use the other one, and evaluate. That's what I thought. And you answered something different. That's what I thought.
The authors are not like specific on how they do this training, but as far as I understand, is that they use this conditioning all the time. So nor is like the probability that I use it. Maybe you know more?
Yeah, so basically.
Oh, wait.
Yeah, so basically this switch only tells us about which condition they are using. So it's not a probability in this case. That would be great actually, because that will resemble a little bit more the glide methodology, but not in this case. If they use, for example, text, then they use the conditioning of text through all the training. So they produce a different model for each task in this case. And another interesting thing, I don't know if you said that or not, is that you can combine different conditionings. So that's also cool. Yeah.
Thank you. And the final is that what the objective function is. So I'm going to try to predict, again, the noise parameterized by some parameter theta, conditioning on the latent space, the time step, and now the representation or the embedding of my condition, which is this tau theta y. And that's
this calligraphic E and D and tau or something that you have before you train this diffusion model, or?
No. Actually, they train tau and the unit at the same time. So this is not a pretrained model. And END are pretrained autoencoders. So yeah, in this part, we first pretrained the autoencoder with the perceptual laws and the patch-based adversarial objectives. Then you use that autoencoder to start the diffusion process and the encoder from the condition.
And then I thought I was like established function, like even number.
Yeah. This is why is parameterized by other parameters. So the authors did a lot of ablations experiments in the supplementary material, but I want to resolve these two. So basically the authors evaluate how was the performance of the generated images with different latent space dimensionality. This number of here is the reduction factor F they use. So the bigger, the lower the dimensionality in the latent space. And the other ablation that I find interesting is see how many steps we have to apply in the diffusion process to generate good images, which are the two crucial parts of the method. How is the dimension of my latent space, and how many times do I have to add the noise in the diffusion process? They at the end conclude that it was better to use a factor size of 4 and 8 and train through 200 steps. But this is just to like the ablation studies of their contributions. But now I'm going to, with the qualitative results, I'm not going to stop in the quantitative because they have a lot of results, a lot of tables, a lot of numbers. But the important thing, sure, please.
The only reason why I know this is because I debug this code, so that's why I know stuff. But something that we found out when we were checking this implementation is that, as you said, they changed the latent size, right? So they tested different sizes, However, what is interesting and what we find out is that the dimensionality of this Z vector is 3 channels. So yeah, we did that same pace because in the end they have Z that yes is the latent of the encoder, but is an image at a lower resolution. And it's not RGB, but it's an image, 3 channels at a lower resolution. So that was interesting because we were like, but then what are they selling? And yeah, they're. Sorry?
Does it make it?
If,
Like delete the channel so that it's just one vector?
no, because the input of the unit is an image. Yeah, that was interesting. Anyways, that's it.
Thank you. So what I was saying about plot. Maybe you can send me through email. No, don't worry. I like that this topic is being passionate about. Oh, yeah. Yeah. So we are going to show some plots of the images in the latent space.
Yeah, so here are these results. So basically we have the method here, right? This is what Christian was telling us. And then here at this point, as you can see, we input in this case, so this is the input, right? We have this woman and we would like to remove her from the picture. So this is the output of the mask zoom with the input image. And this goes through tau, right? And then we end up with this very, very bad representation, let's say. And this one is used as the output of tau, right? And then what this unit receives is Z, which is this one. And then it receives the mask and the output of tau. And then it iterates multiple times. And then at the end, you end up with very nice low dimension representation of this clean version of the image. And then at the end, you use D to decode the output. So it works, of course, yeah, but it was very interesting that at this point, it is only an image at a lower resolution. And yeah, this is how it looks like.
Thank you. So basically we can say that this is like the glide approach, just in a different representation. Yeah. Because of the condition. So can you share your screen again? Sorry. Yeah. So in the conditioning encoder, we have the image and we have a mask. The white part is the part that we want to remove from the image. Then we subtract the two, and then we get this this image with this black spot, and that's what we encode into the tau theta. And also bring the masks in the input through the unit. Okay.
But then if you can use it as a condition factor, doesn't necessarily need to be something, right?
No.
It's just
This is just in painting. Maybe you can like use an image to condition the style of the image. Yeah, what is Picasso style? Yeah.
So that's interesting because the question, I believe the question we asked was, why does it come? Why not add something there?
Yeah.
In this case, your loss function is that this base must be white because you have the mass as well, right? So if you wanted to tell the model, do not delete the movement, but rather add something next to it, what would you change?
There are multiple ways to do that. So, for example, text is one way to they used to add more representations for them to know what to do. But in this case, the task they want to perform with this network is in painting. So, yeah.
So going back to the results, as I was telling you, they have a lot of tables, a lot of numbers, but I'm going to focus in the qualitative result because I think that is the most interesting part of the paper. So this is Celeb AHQ, which is a database composed of different celebrity faces in high quality resolution. And in this task, they are the state of the art in this moment. So these images are all generated images with the diffusion models and are very realistic and have a lot of details. The other task was text to image generation. So this part is interesting because actually they are able to translate from text to image. I don't know if you can see well, but the first example is a watercolor painting of a chair that looks like an octopus. And you see that the generated images are quite good. And the example is a shirt with the encryption, I love generative models. And what I found interesting here is that using DALL-E fails when you use precise text. And this is why I want to show these models, because LDMs are able to use or to generate text or assign text in the images. And this is something that DALL-E doesn't. So in this example, I write a shirt with the encryption, I love generative models. So I want my image have the text, I love generative models. And they like put it in the shirt with a heart. And this is something, if you input through DALL-E, the image, the generated images doesn't have the text. Yeah. We can write text in images. Also, another interesting result is how we are able to pass from semantic images with labels through real images. And another thing that I found interesting is that this is also used in super resolution. These tasks, they don't beat the state of the art, which is SR3. But if you can see here, like the LDMs produce higher details with a better quality, but they fails to reconstruct some particular architectures. So if you can see in, well, I don't know if you can see it here, but maybe you can check the paper. In the wheel, here's some like a lag or a noise, but actually if you see here, they have much more details compared to the other. So LDMs are able to reconstruct higher details, but fails with some particular structures. What? Sorry, what?
Efficiency-wise in time, are they more or less the same? Is SR3 10 times faster?
They did not compare that. So I don't know, but I think that it should be comparable.
So usually generative models, they are one single pass, but with the DDPMs, you have to do a bunch of time steps for it to reach to the results you want. Yeah, it usually takes 1,000 steps.
And how long does one step take? That time, a second?
Yeah, maybe less. But then you have to do that. Let's say you have multiple images. What about you have? Yeah. I'm telling you, it is long.
And well, this is the result. Another that I found really interesting because I already said I didn't see this type of generation. So basically we have a box saying train. Here we have a box saying trees, and the model is able to construct an image from the detection annotations. And I found this interesting. And well, the last qualitative result is in the inpainting part. So if you see, we're actually very good in removing the woman from the chair. Obviously, they have some details, like some waves, but it works pretty well. About the limitations, oh, sorry, yeah, this is what Angela was saying, that despite we are working in a lower dimensionality, we still need a sequential process, which is to add noise t times, and this is lower than GAN's works, for instance, which is the SR3 approach in the super resolution task. And the other limitation is that the generated images can be questionable since they cannot reconstruct the fidelity of some structures, as we see in the super resolution approach. So here we have like a bottleneck of the capability of these models. And to conclude, these models are a simple and efficient way to significantly improve the training and sampling steps for diffusion models. And these models are flexible thanks to the cross-attention mechanisms in which you can condition the generation with whatever data you want. And that's it.